Okay, so let us start the session. You are hearing me okay? Just okay, okay.
Yep.
Well, good. So, according to the rules, let's say I am the president of this committee, but I will not ask questions or not make any comment because this is my role. Only you have to make comments. So thank you, all of you, for accepting. It is an interesting meeting, no? Very international. It is not usual. So many countries presented. So this is good for Julia. Julia disappeared a short time, but Julia, you can start your presentation now and have some 15 minutes, approximately 15 minutes to present.
Okay, thank you, Professor. I'm just going to share my screen. Can you see my slide? Okay.
Yes.
So I think I'll start now. So first, I'd like to thank everyone for being here today, especially the members of the committee. And as you know, I'm a master's student at São Paulo University at the Astronomy department. And this is the work that I did during my master's. So the title is Methyl Acetylene in Degree 1, looking at massive star formation through the lens of chemistry. And my advisors are Professor Jacques Lepine and Dr. Edgar Mendoza. So to start, just a quick introduction. As we all know, the interstellar medium is really brimful of interesting molecules. So there's a very rich chemistry going on there. And those chemical processes, they can be divided into two broad groups. So we have the gas phase chemistry, so processes that happen in the gas phase, and those reagents and products we usually observe in radio wavelengths. So for example, we have reactions involving atomic oxygen and molecular hydrogen that forms OH and atomic hydrogen. But we also have solid phase processes that happen mainly in the surface of interstellar ices. And those types of reactions, we can observe them in infrared wavelengths. But the thing is that the processes that happen in the gas phase and the processes that happen in the solid phase, they are not isolated from each other. They actually are intertwined and they affect each other throughout the evolution of the interstellar objects. And one way that those two kinds of processes are really interconnected is throughout the evolution of interstellar ices. And so in the earliest stages of the interstellar clouds, we have the dust grains that are composed of mainly silicates and amorphous carbon. But then hydrogenation reactions start to occur in the surface of those grains, and they form an ice layer that is rich in water. So we call this the polar ice layer. Then, as the cloud reaches a density threshold, the CO that is present in the gas phase will then freeze out and form this second ice layer that is rich in CO, and we call this the apolar ice layer right here. And then chemical reactions can occur in the surface of this ice, and they are usually induced by some processes such as UV radiation, but even atom addition. And then it forms more interesting molecules, for example, methanol. Then the cloud will continue to evolve, and the protostar or multiple protostars will start to form in the interior of the cloud, and this will heat the environment, And when we reach a temperature of over 20 Kelvin, this is the sublimation temperature of the CO. So this apolarized layer will sublimate to the gas phase, and those interesting molecules will also go to the gas phase. Then, as the cloud continues to evolve and it reaches a temperature of 100 Kelvin, this is the sublimation temperature of water. And so this polar ice layer will also sublimate and will also enrich the gas phase with interesting molecules. And this is the state here where we have all the ice layers sublimated into the gas phase. It happens in this stage that we call the hot core stage. I'm going to talk in more detail about hot cores in the following slides, but that shows that in this stage we have a very rich chemistry in the gas phase. So as I said, in this work, we have used molecular line emission to try to investigate massive star formation processes. And so massive stars, as we all know, they are very massive. So they have over 8 solar masses, and they are very luminous with over 10 to the third solar luminosities. And they play an important role in shaping the structure and the dynamics of the galaxy because they serve as an important energy input in the environment through their stellar winds and supernovae events and etc. And they are also the main contributors of massive elements injection in the environment, and they are also a very important source of ultraviolet radiation. But the problem is that those stars are not very easy to study. First of all, they evolve really fast, so their thermal timescales are below 10 to the 4th years for O-type stars. So that's really quick. And they have a couple of observational disadvantages associated with them. So they are usually associated with very clustered environments, and they tend to be very distant from us. And so because of that, it's not that easy to develop a massive star formation sequence. So differently from solar type stars, for which we do have a star formation paradigm, we are still working on studying the evolution of massive stars. We do, however, have a couple of models that try to describe this massive star formation process. So one of the main ones is the core accretion model, which is basically a scaled up version of the low mass star formation, in which we have this massive clump of gas, and it will collapse to form a massive core, and this massive core will then gravitationally collapse to form either one or multiple massive stars. We also have the competitive accretion model, in which we do not have the massive core. We have this clump of gas, and it will form protostellar seeds, and those seeds, they will then grow by accreting gas from the clump through boundary Hoyle accretion. And finally, we have the protostellar collision model, in which we have the formation of low mass protostars that will then collide in this very dense environment and form the massive stars. Okay, so although I said before that we do not have a massive star formation paradigm, we do, however, have a couple of stages of massive stars that are well defined. And one of those stages is the hot molecular core stage, or HMC. So the HMCs, they are very small sources with sizes below 0.1 parsec, and they are quite warm, so temperatures above 100 Kelvin. They also are quite dense, with hydrogen densities between 10 to the 5th and 10 to the 8th molecules per centimeter cubic, and they are also very luminous and quite massive. And as I said before, in this hot core stage, we have a very rich chemistry in the gas phase, and because of that, those objects, they are associated with a very rich molecular emission spectrum. So the HMCs, they are embedded in those massive clumps of gas. So here I have an image that shows an HMC here in the grayscale, and the contours are showing the massive clump of gas that involves the HMC. And the thing is that the HMCs, they have the same systemic velocity of the clumps, and they also follow the same density profile as the clump. And so what dictates the size of this HMC is actually that We see the HMC as the region where the density and the temperature profile of the clump peak. So the region where we have this peak in density and temperature is the HMC. And this peak in density and temperature is because of the young stellar object that is being formed there. And so we can actually look at the HMCs as the very sites where the massive stars are being born. Okay, so in this work, we have studied a particular HMC, which I'm going to call G331 for the sake of simplicity. And here I have a very nice image of G331 that was observed with ALMA in various different molecular emission lines. And this HMC, it is associated with a very powerful molecular outflow, and it has a systemic velocity of around minus 90 kilometers per second. So from previous studies of this source, we have come up with a physical model to describe it. And so in the center here in yellow, we have the massive young stellar object. And then surrounding this object, we have a cavity of low density. And this cavity is expanding. Then surrounding this cavity, we have a shell of gas that is also expanding. That's because of the stellar winds that are coming from the star. And it is associated with hot temperatures of over 100 Kelvin. We also have the outflows that are coming from the young stellar object, and those outflows, they are closely aligned with the line of sight. And finally, we have an ambient core gas that surrounds everything, and it's not expanding and is associated with lower temperatures, so below 100 Kelvin. So in this work, we have studied molecular emission lines. And to be more precise, we have studied rotational lines. And those rotational lines usually fall in radio wavelengths. And those rotational transitions, they are very important to astrochemistry because around 80% of all the molecules that were detected in the interstellar medium were detected in their rotational lines. So here I have a very nice image that shows that, especially for star-forming regions and for dark clouds, we see that really the radio detections dominate the molecular detections. And those lines, they are interesting because if we have an environment with enough energy to populate the rotational energy levels of the molecule, then we can observe their emission lines. But even if we have an environment that doesn't have enough energy to populate those levels, we can still see the rotational lines in absorption against the background. So virtually, we can observe almost any kind of source using those lines. And furthermore, we know that radio observations are very sensitive and have a very high resolution. And that results in really a forest of lines, as I'm showing you here, that we can observe. So here, the example is the radio spectrum of the Orion molecular cloud, and we can see that really we have a plethora of molecular emission lines that we can study. And so, as I said, we use those rotational lines to investigate our source. And one way that we can do that is through the rotational diagram technique. So for this technique, we first have to assume that the environment is under local thermodynamic equilibrium. And so if that is true, then the excitation conditions of the molecule can be described by only one temperature component. And what this means is that the population distribution of the molecules will follow a Boltzmann distribution. And so if that is true, then this expression here holds, and we can relate the total Coulomb density of the species to the excitation temperature. And then we can start to add a couple more corrections to this formula here. So for example, we can add an opacity correction, which is this term here in the right-hand side of the equation, which basically follows photon escape probability formulation. And it depends on the optical depth of each one of the lines. And then we can start to consider if the lines are optically thick or optically thin. We can also add a beam dilution factor, which is this one in the right-hand side of the equation, which is basically the ratio of the solid angle of the antenna over the solid angle of the source. And it basically takes into consideration if the source is filling the antenna beam or not. And so, if we plot in the y-axis the logarithm of the ratio of the column density of the upper state of the transition over its statistical weight, and in the x-axis we plot the energy of the transition, and if we do that to all of the observations that we have, we should see a linear trend. And from this linear fit here, the slope of the line will give us the excitation temperature, and the y-intercept will give us the total column density. And so in this work, we have studied one particularly interesting molecule that is methyl acetylene, also called propine. And this molecule has this structure here, so it's CH3CCH, and it has been detected in multiple different sources, so including interstellar sources and also extragalactic sources. It is a prolate symmetric top with point group symmetry C3V. And because of the way that this molecule rotates, the centrifugal effects that happen there, they will split the J quantum numbers in multiple K different quantum numbers. So here I have a diagram of the energy levels of this molecule, and we see that for each J quantum number here of rotation, we have multiple rotational energy levels associated with different K quantum numbers. And those structures here are called the K ladders, okay? So this molecule has a very low dipole moment of only 0.75 dBi, and because of that, it is very easily thermalized. And so the LT condition that I mentioned before is easily met for this species. And also because of the selection rules that apply for this molecule, the relative intensities of the different K ladders are dictated by collisions. And because of that, this molecule is a very good temperature probe. So now for the facilities and methods. As I said, in this work, we have studied rotational lines that fall in radio wavelengths. So we have used a radio telescope, the Apex telescope, the Atacama Pathfinder experiment. It is a single dish telescope with 12 meters, and it is based on a prototype antenna from ALMA. So we have used 3 different receivers from Apex. So Apex 1 and Apex 2 from the SHIFI instrument that fall in this frequency range here. So it's basically ALMA bands 6 and 7. And also the SEPIA B5 instrument that falls in this frequency range here. So basically ALMA band 5. So for the data reduction, we have subtracted first-degree polynomial baselines from each particular scan, and then we combined everything together to form the final spectrum. And for the line identifications, we have used databases such as NIST, JPL, CDMS, and the identification criteria were standard. So the peak frequencies of the line should be consistent with the systemic velocity of the source, so around minus 90 kilometers per second. The intensities of the lines should be at least 3 times the sigma of the baseline. And also LT models of the emissions should be reasonably consistent with our observations. So basically, we fitted single Gaussian profiles to each transition, and then we gathered the spectroscopic parameters by that. Then we used those informations to construct the rotational diagrams. For that, we have converted the information from the antenna temperature scale to the main beam temperature scale, and we used the CASI software for that. And also in this work, we have simulated the rotational spectrum of propine, and for that we used the Big-Gopher software, and the Hamiltonian that we used was the standard Hamiltonian here for symmetric tops. So now moving to the results and the discussion. So in this work, we have detected a total of 41 uncontaminated lines of propine, and they were divided in 9 different K ladders. So I'm showing you here in this image all of the lines that we observed. And to the best of our knowledge, this is the first time that this large number of molecular detections were achieved for one particular molecule at one particular source. And so we can say that this is the first spectral survey of propine in this source. And that is nice because then we have a very robust statistics for our analysis. So for the information of the lines, we saw that the average systemic velocity of the lines was around minus 90 kilometers per second. And also they didn't vary very much. So the maximum displacement of those velocities was only 0.68 kilometers per second. And so the systemic velocities of the lines are very consistent with the source. Also, the width of the lines, they varied between 4.15 to 5.68 kilometers per second, with an average width of 4.94 kilometers per second. And so those lines are very narrow. And because they are narrow, we can expect that they are coming from this ambient core region here, this gas that is not expanding. If the emission was coming from the molecular outflow, for example, we would expect the line to be much broader and have extended wings. So to help us understand the analysis that we are going to make in the following slides, I have plotted here in the y-axis the Einstein A coefficient of the lines that we observed versus their energies. And so here in the horizontal trend, we have each K ladder. And as we go up in frequency, so we go up in J quantum numbers, then the energies of those lines, they also increase. And because of that, we expect that the lines with higher frequencies, so the ones that have higher J quantum numbers, they will be usually associated with warmer gas, and vice versa. Okay, so as I said, we have constructed the rotational diagrams for the observations of Propine. And since we are working with single dish data, we cannot say for certain what is the size of the emission. So we started by assuming a source size of 5 arc seconds. And then we constructed the rotational diagram, assuming two scenarios, one where the lines are optically thick and one where the lines are optically thin. And so from the fit of those scenarios, we see that the excitation temperature is from 40 to 47 Kelvin, and the Coulomb density is from 3.9 to 2.4 times 10 to the 15 molecules per centimeter square. And also the reduced chi values are, chi square, are around 3. And first of all, what we see here is that the opacity correction really changes the fit of this diagram. So it is really important here in this case. But what is interesting is that this excitation temperature that we derived of around 45 Kelvin is too low for this source size of 5 arc seconds. So if the propane emission was coming from this compact region of only 5 arc seconds, we would expect the temperature to be much higher, at around 100 Kelvin. And so because of that, we thought that maybe this emission was actually more extended than that. And so we have constructed a second rotational diagram, assuming a source size of 10 arc second instead. And again, we have considered a scenario where the lines are optically thick and one where the lines are optically thin. And then we have fitted those lines, and we derived excitation temperatures of around 47 Kelvin and Coulomb densities from 6.9 to 6.4 times 10 to the 15 molecules per centimeter square. And now we see that the opacity correction doesn't change as much the results. But now we have an excitation temperature of around 47 Kelvin, which is consistent with the source size. So it is consistent with an extended emission. And also the reduced chi square values for this case here, they are smaller than for the 5 arc second case. So the linear fit is better in this case. And from this information, we think it is probably more likely that we have a propane emission that is more extended and associated with cooler gas. And that is also consistent with other observational works of propane towards other star-forming regions. So here I have plotted in the y-axis the optical depths of each line for the 10 arc second scenario. and in the x-axis, the energy of those lines. And what we can see is that, first of all, as the transitions go up in frequency, the optical depth decreases, which is expected, and also that the lines with higher intensity, so the K0 and K1 lines, they have a higher opacity than the rest of the lines. But what is interesting here, what is worth noticing, is that the maximum optical depth that we have is of around 0.2. And so it is reasonable to say that our emission of propine is optically thin. And actually that is also consistent with other observational works of propine. So we have used those information that we derived from the rotational diagram to construct a synthetic spectra under LT conditions of the emission of propine. And I'm showing you here. So in red is the LT models, and in black is the actual observation. And so first of all, what we can see is that for a compact emission here, we see that the LT models of the K0 and K1 lines, they are clearly overestimating the opacity of the lines. And that is consistent with our hypothesis of an extended emission, because since we were underestimating the size of the emission here, then the fit was compensating by overestimating the optical depth of the lines. But now when we move to the extended emission case, then that doesn't happen anymore. And here, what is interesting is that for lower frequency lines, we see that the models are predicting quite well our observations. But then as we go up in frequencies, the models start to become gradually worse. And what's more interesting is that independently from the frequency of the lines, the LTE models always predict that the K2 lines are more intense than the K3 lines. But actually what we observe is that for higher frequency transitions, the K3 lines become more intense than the K2 lines. And so that is interesting because that indicates that we maybe have some problems with the LT assumption here. But nonetheless, all of the LT models are predicting quite well our observations of propine, our identifications, and so we can thereby definitely confirm our 41 detections. Okay, so we used the column densities of propine that we derived from the rotational diagram, and we compared with the column density of hydrogen in the source to derive the abundance of propine there. And we have achieved a value varying from 1.5 to 7.6 times 10 to the minus 8. And when we compare this abundance to other studies of propine in other star-forming regions, so here I have 3 massive star-forming regions here, and this one is a low mass star-forming region, we see that the abundances are consistent with other observational works. But now, going back to that suspicion of the LT condition that I mentioned before, we decided to explore this problem at a molecular level. And so we decided to simulate the rotational spectrum of propine at different temperatures and see how it changes with temperature. And to validate this analysis, what I did was I simulated the rotational spectrum of propine at 300 Kelvin, which is this one in the bottom here in black. And I compared it with the experimental spectrum that was actually measured at 300 Kelvin and is available in the JPL catalog, which is this one in red here in the top. And first of all, the frequency predictions of the simulated spectrum, they are very consistent with the actual transitions in the experimental spectrum. The error is of only around 1.2 megahertz, which is very small. But more importantly, here in the set, you can see that the relative intensities of the lines within each particular K ladder, they are very consistent with the experimental. So that validates what I'm going to show you now. So I have simulated those spectra at different temperatures. So I'm showing you here the K ladders from J10 to J9 for 10 Kelvin, 40 Kelvin, 70 Kelvin, and 100 Kelvin. And what we can see is that the spectral profile of those K ladders it changes very much with the temperature. So here I'm showing you another plot, which in the y-axis we have the ratio of the intensities of the K transitions over the K0 transitions for each particular K ladder. And here in the x-axis is the temperature. And I'm showing you the results for two different K ladders. So in the solid line here, we have the K ladder from J10 to J9. And in the dashed line here, the K ladder from J18 to J17. And those were the two extremes of the frequencies that we observed. And what we can see is that first, at very low temperatures, the K ladders are dominated by the K0 lines. But then as we increase the temperature, the relative intensities of the other lines, they start to increase at different rates. And so at lower temperatures, we see that the K2 lines, they are more intense than the K3 lines. But then as we go up in temperature, then the K3 lines start to increase very quickly. And after this 50 Kelvin threshold here, the K3 lines become more intense than the K2 lines. And that is interesting because that can help us maybe explain our observations. So this phenomenon happens because of nuclear spin statistics. So we have here the propane molecule, and you can see that we have three symmetric hydrogens here. And so because of the nuclear spin of those hydrogens, the rotational energy levels of propane can actually be divided into two different states. So for the transitions with K quantum numbers that are divisible by 3, so K0, K3, K6, and etc., we have the A states. And for the rest of the lines, we have the E states. And the thing is that the degeneracy of the A states is twice the degeneracy of the E states. So the A states have twice the statistical weight of the E states. And so what this means is that, for example, for the K2 lines here, they are E states, and they have a given energy and a given statistical weight. Then the K3 lines, they are A states, so they have a little bit more energy associated with them, but they have twice the statistical weight. And so what this means is that at lower temperatures, we have the K2 transitions here being populated, and we don't have enough energy to populate those K3 lines. But then as the temperature increases, we start to populate this K3 level here, and it will, its intensity will increase very quickly because it has 2 times the statistical weight. And so that is interesting because we actually observe this happening in our observations. So for lower frequency lines, we see that the K2 lines, they are more intense than the K3 lines. But for higher frequency lines, the K3 lines here, they become more intense than the K2 lines. And to try and quantify this phenomenon for the whole spectrum, I have plotted here in the y-axis the ratio of the areas of the K2 lines over the areas of the K3 lines for each particular K ladder. And here in the x-axis is the J quantum number of those K ladders. And since the widths of the lines, they don't change very much, we can directly correlate this to the intensity of the lines. And what we see is that really we have a very strong negative correlation here with a Pearson correlation coefficient of minus 0.84. And so indeed, we are observing in our spectra this inversion occurring. And that is interesting because that indicates that likely our observations cannot be explained by only one temperature component. Instead, they maybe should be described as being under a temperature profile. And so to explore this temperature gradient hypothesis, we have constructed modified rotational diagrams. So if you remember, in the traditional diagram, we have in the x-axis, the x-axis here is under linear scale. And then if the emission is under LTE, then for this traditional diagram, the fit of the observations should be linear. But if our observations are not under LTE, so if they are not described by only one temperature component, but instead they are under a temperature gradient, then this traditional diagram will no longer be linear. But what Mossberger and co-authors have shown in this work here is that if we have this, this scenario where we have a spherical cloud and it has a temperature profile that is a power law with relation to the center of the cloud, if that is true, then a modified rotational diagram in which the x-axis is also in logarithm scale, it should be linear. In this case, it should be linear. And so we have explored it, and we have constructed those modified rotational diagrams for all of the scenarios that I talked about before. And what we saw is that actually the reduced chi-square values for our linear fits in all of the modified diagrams were systematically smaller than the fits for the traditional diagram. And so the linear fits are better for this modified diagram than for the traditional diagram. And that also points in the direction of a temperature gradient. And so to try and maybe quantify this gradient, I have constructed again the rotational diagram, but this time I have separated the lines into two subsets. So we have first this lower energy subset here, which has the transitions with lower frequencies that should be tracing the cooler gas. And we have also this higher energy subset here, which has the transitions with higher frequencies that are tracing the warmer gas. And so from those fits, what we saw is that for this cold component here, the excitation temperatures are around 40 Kelvin. And for this hot component, the excitation temperatures are around 60 Kelvin. And that is interesting because although the original rotational diagram, the traditional one with all the 41 lines, seemed very linear and very under LTE, in fact, it can encompass this temperature difference of 20 Kelvin, which is not very much, but it falls exactly in this region here where we see the temperature inversion occurring. So for the cold component at 40 Kelvin here, we would expect to see the K2 lines more intense than the K3 lines. But for the hot component at around 60 Kelvin, the K3 lines become more intense than the K2 lines. And so that is interesting because that shows us that because of the molecular properties of propane, we can even assess the small scale structure of our source, even though we are working with single dish data. And also, via SkyMapo, they have observed propane in GT31 using ALMA, and they have observed 4 lines of propane there. So those 4 lines were in the K ladder from J21 to J20. And their observations yielded an excitation temperature of around 70 Kelvin. And this temperature, this result is also consistent with our hypothesis, because since they observed lines with higher frequencies, we would expect those lines to be associated with even warmer gas. So now going back to the LTE models of the lines, as I showed before, the LTE models were predicting much better the lines with lower frequencies than the rest. And those models, they were constructed using the information that we gathered from the rotational diagram. And so what this is showing us is that likely those models, they are biased towards the lower temperature gas. Okay, so now moving on to kinematics. As I said, we have observed those lines with single dish data, so we don't have high angular resolution, but we can still gather some information on the kinematics of the source using the spectroscopic parameters of the lines. And so we did that. So I'm showing you here in the y-axis the systemic velocity of the lines, and the x-axis their frequencies, and I have separated the lines into in their k-contour numbers again, just to help with the analysis. And what we see here is that indeed all the groups show a very strong negative correlation here. And so that is interesting because, first of all, it shows us that the different lines with different frequencies are indeed tracing slightly different gas. And that the lower frequency lines, which are associated with colder regions, they are slightly redshifted. And the higher frequency lines associated with hotter regions, they are slightly blue shifted. Okay, so now moving forward, I have plotted here in the y-axis the widths of the lines, and in the x-axis the frequencies of the lines. And what we can see is that, again, we have a positive correlation here. In most cases, a strong positive correlation, but nonetheless, all of them show some correlation. And especially the K0 lines show a very strong positive correlation, which is almost a linear trend here. And so what this shows us is that those higher frequency lines, they are systematically broader than the rest of the lines. So those warmer regions, they result in broader lines. And this cannot be explained only by the Doppler effect, because the Doppler broadening doesn't contribute as much to the widths of the lines in radio frequencies. Instead, what should be explaining this broadening are turbulence effects. And so this is not a very strange assumption to make, because since we are talking about warmer regions, they should be more compact and closer to the young stellar object. And so it is reasonable to think that they are also more turbulent. So here I'm showing a combination of the two plots that I showed before. So in the y-axis, we have the width of the lines, and in the x-axis, we have the systemic velocities of the lines. And first of all, what we can see is that indeed all of our groups, they show a strong negative correlation here, and that was expected because of the previous plots that I showed before. And so that indicates to us that indeed the warmer regions, which are associated with the broader lines with higher frequencies, they are slightly blue shifted. But what's more interesting in this plot here is that the K0 lines are slightly displaced from the rest of the lines. So they show a slightly different kinematic signature. And since we don't have high angular resolution, we cannot say for certain why we are observing this plot here. But we can speculate as to the reason behind this. And so what we think maybe is happening here is that if you remember, the K ladders at lower temperatures, they are dominated by the transitions, the K0 transitions. And so what we think is that possibly those K0 lines here, they are actually tracing a different gas components than the rest of the lines. So cooler and more extended gas component. And because of that, they are displaced from the rest of the lines. Whereas those other lines, they are tracing a warmer gas component. But as I said before, we really do need higher angular resolution to investigate this conclusion here. So now to finalize the conclusions and future perspectives of this work. First of all, as I said before, this was the first spectral survey of propane towards G321. We have detected 41 uncontaminated lines of propane, which is a very large sample. And we have constructed rotational diagrams to derive the excitation temperatures and the column densities of these species. And from this analysis, we expect the emission of propane to be coming from a cool and extended region. And this is also consistent with other observational works of propane towards other sources. Also, we derived the abundance of propane in this source, which is around 1.5 to 7.6 times 10 to the minus 8, which is also consistent with other observations. And we have inferred that this gas is actually under a temperature gradient with a lower limit of around 40 Kelvin and an upper limit of around 60 Kelvin. And this analysis was interesting because it allows us to assess the small scale structure of the source, even though we are working with single dish data. The kinematics analysis showed that the width of the lines and the systemic velocities of the lines are correlated with their frequencies. And so that shows that the different transitions were actually tracing slightly different gas. And it shows that the warmer gas, which is associated with the higher frequency lines, it is slightly blue shifted and more turbulent. And the cooler gas, which is associated with the lower frequency lines, is slightly redshifted and less turbulent. And also, we saw that the K0 lines have a slightly different kinematic signature than the rest of the lines. And what we speculate as to the reason why that is because we think that the K0 lines are actually tracing different gas components than the rest, a more extended and cooler gas components. So now for the future perspectives. First of all, there is a forthcoming paper on the results of this work that is at an advanced stage and just need a little bit more revising, and then it should be good to go to submit. And as I said consistently throughout this presentation, we do need higher resolution to properly validate our conclusions. And so it would be interesting to write an observing proposal to maybe ALMA to try to explore this more deeply. And last but not least, it would be interesting to maybe construct some theoretical models using chemical networks to try to correlate the abundance of propines to other relevant molecular species in the source and try to explore the chemical evolution of the source and the age of the source. And that's it. Thank you very much.
Okay, thank you very much, Julia, for your presentation. Nice presentation on keeping in very good time. So I wonder if some of you want to have a rest, a cup of coffee, or yes, you 1 minute of walking around, and then we come back, okay?
Okay.
Okay.
I'm going to grab a cup of coffee. I'll be right back.
Yeah. Just Okay. So the order of the people to make comments, we used to take the most distant one first, and so I will ask Bertrand to make his comments and questions.
Okay, Jacques. Can you hear me?
Yes.
Yeah. Yes.
Yes.
Okay. So before starting, just some general comments. I liked very much the presentation you gave. It was extremely clear and very synthetic, really very nice. And I found it complements very well the manuscript that you have written, and which is, I find, I was quite impressed by the quality of the manuscript, I must say. The quality of the introduction that you in this manuscript, it's quite rare, at least for European people, to see a manuscript at this level of master that covers so many different aspects and many different fields of molecular astrophysics. And I enjoyed it very much, and I congratulate you for all the work you did and so many different tools that you have used to carry out this piece of work. It's very detailed analysis that you have really been, I would say, almost up to the limits of what can be done with single dish observation. So this is really a very nice piece of work, and congratulations again.
Thank you.
So of course I have many questions, and I could probably keep you busy for many hours, but I don't think it's really the goal of this meeting. It was just a few questions I would like to discuss with you. So you mentioned, for instance, it's an interesting point that you find in the end that the CH3CCH, this abundance, the abundance you derive, seem to be quite similar to those measured towards at least a few other hot molecular cores. From what you shown in this presentation, but you did not give an interesting parameter, that is the luminosity or the age or the evolutionary status of these other cores. So are we talking of completely different objects, or are we talking of objects at different stages or in different environments?
No, in this presentation here, in the table that I showed you, they are all HMCs that are quite similar to G31, but a little bit more evolved, right? Because the source here, we believe, is very young, but they are all in massive environments, and I cannot say for certain the value of the luminosities, but they are really quite similar to G31 in that aspect. And also in the dissertation, I haven't shown it presentation, but in the dissertation, I also mentioned a work, I believe is from Gianetti, but I'm not sure, the author, in which she has explored, I believe it was around 50 different hot molecular cores, so massive objects, those massive young stellar objects that I mentioned, and she also found similar abundance for all of them. So the average abundance was also in the order of 10 to the minus 8 for those sources that were, she included different evolutionary stages, all within the HMC stage for massive star formation. And
okay,
so yeah, so I think this abundance doesn't change very much with the age of the source.
So which is quite an important result for the chemistry of CH3CCH. So in that sense, how would you explain the fact that the abundance you measure, that is measured towards L1527, which is a low mass star forming core, is significantly less? How would you explain that?
Yeah, I'm not. I was wondering about that also. I'm not certain as the reason why this is happening, but I imagine that maybe it has something to do with the solid formation of propine, because actually when we see the theoretical models of CH3CCH, when we include only the gas phase processes that form this molecule, the abundances are actually very much lower than the actual abundances that we observe. I believe they are around 10 to the minus 10 or minus 9, which is quite close to the low mass stars. But then when we include ice surface reactions, then we start to see this abundance increasing. So that's why there's this discussion that maybe the propane formation is also, it's important to consider the surface reactions. But the problem is that exactly in this paper that I mentioned, of I believe it's Gianetti, they showed that the abundance of propane doesn't change very much with the age of the source, with the warm-up of the source. So what they mentioned there in this work is that probably if the propane is being formed in important quantity in the ice, they should be effectively sublimated at temperatures of around 20 Kelvin. And so I believe maybe that's something to do with that, but still there's some problems, because even at low temperatures, we should have the masses, I mean, we should have this 20 Kelvin ice sublimated. We should have this polar ice that sublimates at 20 Kelvin sublimated. So we should have this high abundance at, we should have this contribution from the ice. But nonetheless, here I'm only presenting one result from one low mass star formation region, whereas for the massive star formation, we have multiple results. So maybe it's a question, it's an issue with the sample size.
Okay. So we can talk later about.
Yes.
I had a naive questions about the line opacities, and you spent a lot of great care in analyzing the effect of the optical depth on the profiles and the analysis of the rotational diagrams. And it was not clear to me whether there were some rare isotopologue transitions in the spectral bands that were covered with APEX. I understood that you did not detect.
Yes.
That you did not have. But could you place an upper limit on the line of the intensities of some transitions, in which case that would allow you to place some constraint on the optical depth of these transitions?
Yeah, this is something that it would be very interesting to do. We actually did not place this upper limit in the abundance of the possible isotopologues that were there, because it was a matter of time. We didn't have enough time to go through this direction. But yes, we do have a couple of lines there that we believe that maybe they are associated with the isotopologues, but we didn't have enough time nor enough sample of lines to confirm those detections. And also they were they had a very low intensity, and they didn't match this 3 sigma threshold there that I mentioned. But it would be interesting to use this information to propose this upper limit to the abundance of the isotopologues for certain.
Okay. Well, I stop here, and if later, if time allows, then I would be glad to come back for other questions. But thank you very much for this very nice presentation and for this very nice piece of work.
Thank you very much, Bertrand. Merci beaucoup.
Okay, let's fill the void. Just a question in a different aspect, Julia, concerns the observations with Apex. I understood that these observations were carried out in position switching or on-off observing mode, which consists to observe the source and then move to a reference position at a given distance. And as you have seen from your work, that some transitions of CH3-CCH can be more extended than others. And in the end, when you see it from, as you show in your introduction, is that CH3-CCH is very easily synthesized, present in all kinds of different environments. And could it be that actually, did you check that the off position was actually free of emission, free of CH3-CCH emission? Yes, and if no, do you think it could alter or introduce some bias in the analysis of the data?
That is a very interesting point. I have not thought about that, but for certain we should investigate if there's propane lines in the off position. I think that this is a very ubiquitous molecule, right? So there is some chance that we actually have some contamination there. Nonetheless, I don't think it would show, it can be biasing our results if this hypothesis is true. So it is worth investigating. But the main points here, they are clear trends that I do not believe that one contamination would result in those trends that we see, in those correlations that are really spread out throughout all the frequencies that we observed. But yes, for certain, we should investigate this question. Thank you.
Jacques is back, I think. No?
Posso mandar, mas eu não tenho o telefone dele, eu só tenho o e-mail dele. Mas tudo bem, porque eu acho que a gente pode, o Edgar tá aqui, ele também é meu orientador, então acho que a gente talvez possa.
Okay, yes, I can try. Jacques is here again. So Jacques, can you hear me?
Okay. Sorry. Yes. You know, I was off for a moment, and so I didn't know what to do. I was touching everywhere, but now I am back, no problem. And so, Bertrand, you have concluded your comments, I understand. Yeah. So let us go now and ask to Leonardo to make his comments and questions.
Okay, thank you. Do you hear me well?
Yes.
Yes.
Fine. Then, first of all, I would like to thank you for the kind invitation to form part of this committee, and give my congratulations to Julia, because I think it's a very good thesis with a fairly complete introduction to the theory and methodology, which will be a good reference for other students. The observations themselves are treated with high completeness, making the best use of the available data and obtaining solid results. So please have my congratulations.
Thank you.
Okay, now as for the comments and questions, first of all, I have a small comment which is a bit unrelated to a complete thesis, just one example that you put in section 1.2, figure 1.3 of the thesis, the massive star formation NGC 6334.
Okay, I'm getting there. Yes.
Yeah. Okay.
Okay.
How come that the separation of the clamps within a filament, which is 0.7 parsecs, is smaller than the clamp sizes, which is 1 parsec? That I didn't understand.
Yes, I also I noticed that also, but this work was very recent and they used very different data from all sorts of places to construct this final image. So I'm not entirely certain as to this reason also, but I nonetheless thought it was a very nice image to show this certification of the structure. So that is why I put it there. But it really, I have some problems with the scales also.
Okay. Now going to the thesis itself.
Okay.
You say in section 1.3.1 that the radio source G331.5 is located at the tangent point of the normal spiral arm in the southern galaxy at a distance of 7.5 kiloparsecs. And it consists of an extended, exceptionally luminous and massive region of ionized gas with a far infrared luminosity or so and so, and a total CO mass of the order of 10 to the 7 solar masses.
Yes.
And the question is this the mass? You define the ionized region. Is this the mass of the ionized region within a few parsecs, or of the full GMC of a few tens of parsecs?
Yes, I'm just trying to find the exact value again to make sure.
1.3.1.
1.3. Okay. I believe this is the mass of the clump, right? The other region, right? Because it's very high to be just the mass of the.
Sorry, can you repeat? I didn't hear it.
Yeah, okay. I believe this mass that I mentioned here of 1.4, right, times 10 to the 4 solar masses is the mass of this dust concentration, so maybe the clump. Because if it was just HMC, I think it would be too massive, right?
Yes.
Okay.
So this 8.7 times 10 to the 6 solar masses is the mass of the giant molecular cloud.
Okay.
Complete.
Yes. The giant. I thought he was talking about the other mass I mentioned before, after that, of the dust continuum observations. No, this other one is the cloud. Yes, it's too high.
Because you say you define it for the ionized region, and I think that's probably not totally correct, because this is the mass of the giant molecular cloud.
Yeah, I definitely should have phrased it better. I will correct that.
Yeah.
Okay.
Also, just to comment that this you do, our hot core is part of a collection of 6 bright sources at the very center of the giant molecular cloud, which has that mass.
Yes.
And then again, can you, about the GMC, which is a parent cloud of our hot molecular core and outflow, can you expand a little bit on the location of the parent GMC in the galaxy? For instance, its distance to the galactic center, its galactocentric radius, and its size and mass relative to other GMCs. I mean, is it an average GMC? Is it large? Is it small?
Yeah, I know that it is close to it's closer to the center of the galaxy because of the distance, so it should be more towards the center. But I'm not entirely sure if this is a unique massive cloud. I'm not sure if this is if the mass or the luminosities are different from the average. I don't believe it is, just because if it were, I would expect maybe to see that really clear in some of the works that I read. But for certain, I should check if I should check the values for the other environments to see if that is true or not.
Well, it happens to be one of the largest and most massive GMCs in the galaxy.
That is very interesting. Yes. But now that you mentioned, I remember that I read that it is very luminous, right? The source. So I believe it is a very
Yes.
luminous source. Yes. Now that you mentioned, I remember this. It is true.
Yeah, perhaps you could say something about that, because
Yes.
over there, the galactocentric distance of the giant molecular cloud is about 4.5 kiloparsecs. So it's about midway between the sun and the galactic center. And as that, it is in the so-called peak of the molecular annulus, or molecular ring. And also it's in the peak of the massive star formation ring. So that's what I wanted to stress that could be useful for you.
Yes.
For the paper, for instance, to state that it's in a very particular region of the galaxy where it is likely that the most massive stars are being formed, and you have the most luminous outflows too.
Okay. Okay.
Okay.
I'll incorporate it.
Yeah, that's one issue. Then, about the kinematics. In the 3.4.1, you say the lines associated with colder regions, i.e. with lower frequencies, are characterized by more redshifted velocities, whereas warmer regions seem to be systematically blue-shifted. I understand well that the full width as our maximum versus frequency should vary because of the turbulence. But can you say something about the geometry and the distribution of the colder and warmer gas regions?
Yes, there was a point that I was wondering throughout all this time, because it's a little hard for me to try to explain these resultant velocities in terms of the morphology of the source, because we have this. Let me try to get to the model here again. A little far, but we're getting there. Yeah, here. Okay, so as I said, we expect the emission to be coming from this shell of gas here, the extended one. And we are looking this way, right? So what I believe maybe can explain those velocities is that the warmer components that are getting closer to us, we are looking at regions maybe here in this gas that is expanding towards us, and the other part of the emission, the cooler part of the emission, is maybe we are maybe seeing more of this region that is going away from us. Now, how those two correlate with each other in a way that we see this I mean almost linear trend is still an open question to me. But I believe that maybe it's I know that the shell is we are closely aligned with the outflows, so maybe we are looking, the outflows could be maybe interfering a little bit with these warmer components, but I'm really not sure. It's an open question for me.
Maybe it could be also considered that the emission, at least as seen in ALMA, is quite clumpy for this velocity component.
Okay.
The low velocity, the low line width component. So that may have something to do with it.
Yeah, I believe so, but I would like to explore this deeply. I also believe that with high angular resolution, we could go to the bottom of this question also.
Okay. I have the last question now.
Okay.
You say in 3.4.2, when you explain the full width, half maximum versus frequency, you say that instead the line broadening is likely to be caused by turbulence effects. In other words, the broader widths associated with IAG values indicate that the gas where the bulk of the emission arises from must become gradually more turbulent as the temperature increases. Okay, this is 3.4.2. So as I understood, this is an indication that the higher J values, higher frequency values get exacted closer to the continuum source. So in the ALMA data, we have the transition J21 to 20, K equals 0. And the size is about 5 arcseconds, where you took the 5 arcseconds. As measured, this is, as we take into account that this is measured in band 7.
Mm-hmm.
So can you predict from your results that the source size measured with higher resolution with ALMA at lower bands should be larger than 5 seconds? Can you predict with some level of certainty for a proposal?
Yeah, I don't think, well, I think that maybe when we have, in this hypothetical scenario where we have observed with ALMA this wide range of frequencies, and then we finish working with the data and we have this final spectrum that is convoluted and everything, I believe that maybe I think we could expect that the emission would be more extended for the lower frequency lines. But the problem that I can maybe see arising here is that I'm not entirely certain how to work with interferometry data. But I know that because because we have this high angular resolution, we do have a smaller flux of intensities in those lines. And I don't know if maybe when we make this convolution process, if this could influence in the analysis of the extension of the emission as a function of the frequency of the lines. So that maybe there's a problem there. But looking just at the theory, I believe that in theory, the lower frequency lines should be more extended than the high frequency lines.
Yeah. And when the last question is, in this ALMA proposal, which you plan to present, what else could be included as a goal in the ALMA proposal? For instance, how could you study the outflow itself, which is one of the strongest ones observed, apart from what has been done until now?
Well, okay, so I'm not sure how to answer this question because the propane is not actually in the outflow. But maybe we could, as this shell of gas gets near the outflow, I would expect, first of all, that the lines would be more warm, and also that they would become gradually broader. So maybe we could try to investigate this in this direction, which is closer to the source per se. The lines are broader because of the turbulence, but then as they go closer to the outflow, they become broader because of the collisions with the outflow. So that is one way I could think right now at the top of my head.
Sure. Well, no, this is because it is important to continue with this research with high resolution. I find that your case for an ALMA proposal is very well stated, and that's why I'm trying to call your ideas
Okay.
make it stronger. So thank you very much, and that'll be all for me. And,
thank you very much.
Congratulations again.
Okay. You're muted, Jacques.
Okay. Now I am. First, well, I come back. Leonardo, thank you for comment station. And Edgar ended his comments if I thanked him or not, because I was a little in a hurry about it. But I thank you both, and now I pass the comments and to Amaury. Amaury, can you make any comment, any question? Microphone. Yes, I am with the Realtek microphone. Yeah. Yeah. So what should I do? Well, I'm always there now. Great.
Okay.
Okay, Amaury.
Okay.
Okay.
So I'm supposed to speak now, right?
Yeah.
Right, Jacques. Okay. I want to clarify one point here. Is that I was assigned by the graduate school in astronomy program to follow Julia's progress in her project and to report on that to the department. On the other hand, her co-advisor, who's Edgar, was in the same situation as far as graduate school is concerned, and I also was assigned to be the one to make reports on his progress, on his work to the department. So we have a cycle, and I didn't have actually to make questions to Jacques or to Julia, because just my next door I had Edgar, and I could follow step by step the development of Julia's project and also the work of Edgar himself, right? Plus the quality of Julia's reports, written reports. I believe it was about 3 reports during her master's that I read and reported on. It was outstanding, of outstanding quality. The English, the level of the theory, exploratory theory, the theoretical plus the observational quality of the work. So I was not quite surprised by the quality of the thesis that she presented in the very end that she showed us today. The quality of her presentation introduction was also the best. And I really don't have specific questions to make to Julia. What I do have are some remarks or minor comments that will certify that I really read the work. Okay, I have it printed. I have it printed, and I read it all the way down. Okay,
Okay.
I don't know if you noticed that I just said master's thesis. I didn't say master's dissertation. I don't know who make this arrangement or mess or this classification here in Brazil. But here in Brazil, what we call thesis is PhD work. And what we call dissertation is master's work here in Brazil. Abroad is the other way around. You say master's thesis and you say PhD dissertation. So if we follow this tradition that we brought it from overseas, you would have to make this very small change since your acknowledgements up to future perspectives all the way down, and make it opposite, where you say dissertation should be thesis. Okay? So that's a curiosity.
Okay.
Now, let's go to page 24.
Okay. Almost there.
Okay, right in the first paragraph. You found it?
Yes, yes.
This is something that if you ask here to the thesis committee members, each one is going to end up or present a different number for the number of molecules that actually have been discovered, right? Your number here matches with mine from the literature. You say, to date, nearly 200. I have 204. It's the same number, right?
Yeah.
What they should be, you should write here. To date, nearly 204 individual molecules, comma, comprising of 16 different elements, comma, have been definitely detected. Notice that I deleted tentatively detected,
Yes.
because it's ambiguous, tentatively or definitely detected. For us, it's normal, but if you give this one, this work for someone who are not in our field, you know, he's not going to be clear what really was detected, what was tentatively detected, right?
Yeah.
Now let's
Okay.
go to page 27.
Okay.
Those minor corrections I can give you later on written, okay?
Okay.
But what I'm doing is just to show you that they should be done. In our
Okay.
page 27, in the section 1113, first paragraph, you give an example of a chemical reaction, right? C++
Yes.
H2O.
Yes.
You should give it the products.
Okay. Yeah, I can.
H2O, HCO plus H,
Okay.
right? And you can do the same thing with sulfur. Should be C plus 2 plus H2S, giving you HSC plus H. So you have another alternative, right?
Okay. Yes.
Now let's go to page 56.
I'm here.
Everyone here is very pleased with your lightweight to write and the quality of your English and of your scientific work. Everybody agrees with that. And my feeling is that since reading your previous reports and now the thesis, you have a very nice, a very sensitive way of trying to write in a smooth way, so that one person won't take your work to read. No, it's not something boring. It's something very light. You avoid some equations that would be boring for someone to see or to read, okay? But in your second paragraph here, you say, the signal received from the sky is converted from the telescope count units to units of antenna temperature, TA. Okay?
Yes.
You do not define in the entire work what's the antenna temperature.
Yes.
And here there's no way to avoid it. You should put here the definition of TA with the double integrals, you see, in azimuth and elevation. Okay? So that in the third paragraph, when you say the antenna temperature TA, you already define it in the top. Here, there's no way out. You should give it the formula. Okay?
Yes. No
Let's
problem.
go to page 65.
Okay.
Okay?
Yes.
In this nice table where you give the J number, you give it the projection, the K number, I think that you should put a note in the bottom of the table, okay? And this note should be just to give what you have in the top, you see, in a footnote, you know. So it's going to be E, AIG, and the other elements that you have here. You see as the antenna temperature and so on.
Okay.
Okay?
Yes.
Now, on page 75, you already clarified in a message
Yes.
that you changed.
Yeah, I switched. I'm sorry. Honest mistake.
Okay? And my final comment is that what was surprising to me and was very nice to find out is that Julia has an outstanding knowledge of rotational spectroscopy. Okay, this is not common among our students for MS or PhD level. Okay, she's a chemist by her BSc degree. She's not a physicist, but the conclusion is that this knowledge, she brought it with her before starting our work here, or her work with Jacques and Edgar. And as a result of this, she have already 2 papers, published papers from last year, you know, which testify what I'm just saying, you know. This knowledge is outstanding to me. These are my comments, my remarks, and once again, Julia, I was very pleased to track. Let's work the word track your work and the output, the final output of the work. And congratulations once again.
Thank you very much, Amaury. I really appreciate it.
Thank you, Amaury, for your comments and yes, all your remarks. It was quite good. And let us say, I believe that Edgar is like me. He's considered as an advisor, and so he should not make comments on questions now.
Oh yes, yes. I would like to say to send congratulations to Julia for this work and for her efforts during this year. a very terrible time. So congratulations, Julia. Very nice work. This is all that I can say as co-advisor.
Thank you.
Thank you. And well, I also think that it was a very nice work. She works very well, and she works alone practically. Of course, we have very, very little. She was very, very good. Now, concerning the bureaucracy, the main paper that Julia needs, the acta of the defense of Internet, I was told that I can sign it by myself. Then, yeah, yes, yes, with the translation. Well, I think it could be. Let
Yes,
us accept him. Yeah.
yes. I can participate. Um, Richard, just I need to do that, or just Jack?
So,
Okay.
okay.
So I'm going to stop presenting. Mhm. Tá, tá. Obrigada. Obrigada.
let us wait for the others. They are coming from the other room and arriving.
Okay, here we are.
And
Where is Leo? Leo is. So this is the new normal in these pandemic times.
Yeah.
well, I think that Leo liked that room.
Okay.
Okay. Now here we are.
Okay, thank you.
Okay. We passed a short time in the other room, Julia, and we discussed and we decided that your thesis is approved.
Yay!
This is unanimous, and all of the members were very, very happy with your thesis or dissertation. I don't know yet. The idea of
Thank you. Thank
so
you.
I will send you today the needed papers for your. When do you expect to travel?
So to the Netherlands.
Yeah.
Yeah. So I'm still not sure because I need my visa to be ready, and it's still I'm still waiting for my visa to be ready. And once I have my visa, then I will travel there. So I expect something between March and April.
Okay. Okay.
Whom are going to work with, Julia?
I'm going to work with Professor Harold Diners in the Laboratory Astrophysics department. So it's going to be more of experimental work. But I hope to be able to make some collaborations with the observational groups also, and try to approach these questions in a more holistic manner.
I did not understand, sorry, which institute is it? Is it in Leiden that you're going to?
I'm sorry,
or-
I thought you said advisors. Yeah, it will be Leiden University.
Okay.
And did you got your vaccine? Or not yet?
Me?
He didn't hear me. So,
I hope so, but not yet.
but Leonardo, did you got your vaccine? No answer. So let us stop the session is over, let's say, and.
Okay.